The 10th question that we have is a very conceptual and a very important problem. You can clear all your confusions about Doppler effect from this question. We have been given a cart which is moving with a velocity Vs towards right side. The velocity of the medium that is there is given Va towards the left side. This cart has a horn which is blowing with a frequency f, and we have an observer which is in front of the car and moving with a velocity V0 towards right, and there is a wall in front which is moving towards left with a velocity Vw. We need to find out the wavelength and the frequency of reflected wave as observed by A. Now, we know that in the case of reflection, the number of wavelengths incident per second on this wall is equal to the number of wavelength reflected per second by this wall. This is the rule, remember this. So therefore that means the frequency incident on the wall is equal to the frequency reflected by the wall. Always remember this, that the incident frequency is equal to the reflected frequency. So what happens after reflection is that this wall starts acting as a source of frequency Fr. Now, for finding out the frequency reflected, we first have to find out frequency incident on this wall. The frequency incident on this wall is equal to the frequency observed by an observer. If the observer is moving like the wall, that is, you treat the wall like an observer and find out the frequency observed by this wall. That will be the frequency incident on this wall. So let us find out that frequency Fi. Now in this question, speed of sound is V. It is given to be V. Now, to find out frequency incident, this is the source for this observer. When we treat this wall as an observer, this is the source. So we can write lambda observed by this wall into frequency observed is equal to velocity of sound with respect to observer, that is the wall in this case. So on substituting the values over here, the lambda observed will be the lambda sent in by this cart, by the horn on the cart. So the lambda sent in is equal to V dash, that is V minus Va minus Vs into T, that is 1 upon F. This is because sound travelled here with V, but since the velocity of air is Va, we subtract Va. Therefore the net speed with which sound travels in this direction is V minus Va. Now again, since the source is moving in the right direction with velocity Vs, therefore it is always V dash minus Vs into T minus Vs, where V dash is the velocity of sound with respect to medium. Now we have got the wavelength observed by the observer. Now we need to find out the velocity of sound with respect to observer, that is the wall. Therefore this will be equal to V minus Va, that is the speed with which sound is actually coming, plus we will add the velocity of observer by inverting it, that is Vw. Therefore on substituting the values over here, we get V minus Va minus Vs upon F into F observed, or rather F incident. This will be equal to velocity of sound with respect to observer, that is V minus Va minus plus Vw. Therefore we can write F incident is equal to V minus Va plus Vw upon V minus Va minus Vs into F. Now we know the frequency reflected by the wall, that is equal to Fr. Now treat this wall as a source of sound. Now we know that it will emit sound in this direction, that is, it will reflect sound in this direction. Now since this is a source and it is moving towards the observer, therefore we can again write the equation for the lambda which is sent out by the wall. You always find out the wavelength from the equation of the source. So the lambda sent out by the wall will be equal to V upon, that is velocity of, this is V plus Va minus Vw. This is because sound travels in this direction with V plus Va, because it was V in this direction and Va gets added to it. V plus Va minus Vw, because the wall is travelling in the direction of the source, in the direction of the observer. The observer in this case is A. So the wavelength emitted is V plus Va minus Vw into T. T dash, this is T dash nu. T dash can be written as 1 upon Fr, that is frequency reflected. So on substituting the value over here of Fr, we get V minus Va plus Vw and on the numerator we get V minus VA minus VS, and we get a F here. So this is the value of the wavelength which is observed by A, because the wavelength observed by A does not depend on the speed of A, or does not depend on the speed of A, it depends on what is the wavelength sent by the source. So this is the wavelength observed by A. So we now need to find out the frequency observed by A. So the frequency observed by A can be written as, for an observer you can always write this equation, lambda observed into frequency observed is equal to velocity of sound with respect to observer. Therefore lambda observed we already know, this is equal to this quantity. So frequency observed, velocity of sound with respect to observer A will be, sound travels in this direction V plus VA. For finding out with respect to A, we invert the velocity of A and add it to this to get V plus VA plus V naught. So now on substituting the value of this lambda observed over here, we get the value of F observed to be equal to, F observed is equal to V plus VA plus V naught upon lambda observed, that is upon V plus VA minus VW, V minus VA minus VS into V minus VA plus VW into F. So this is our final answer for the frequency observed by the observer A, and this is the final answer for the wavelength observed by the observer A. So the important thing for you to note is that whenever you are trying to find out the wavelength observed by the observer, then you have to write the equation from the part of the source, and when you need to find out the frequency observed by the observer, then you always use the formula lambda observed into F observed is equal to velocity of sound with respect to that observer, and so we get our final answers.